We can get started with Chapter 28, Amplifier Basics. And this is really our second chapter in analog circuits. Up to this point in ELEC 120, we studied a variety of solid-state semiconductor devices. And for the first time last week, we put these devices into a circuit that actually did something for us. And what we studied was the power supply. And the power supply, of course, is a combination of a transformer, rectifier circuit, filter circuits, and then finally we talked about regulators that keep that output at a constant level. And the interesting thing about a power supply is indeed a real circuit. A lot of what we've been talking about thus far, including ELEC 110, you probably recognize that problem on the board. That was a fictitious circuit. I mean, a company doesn't go out and build circuits like that. There's no money in building circuits like that. They may build a circuit like that for the purposes of building an electronics training unit, but that's not reality. A power supply, on the other hand, is reality. Those are real circuits that exist out there to give us the DC values that are needed to properly bias solid-state semiconductor devices. The circuit that we're going to talk about today, amplifier basics, again, are real circuits. Amplifiers are real circuits. They exist out there. So all of this is very contemporary information that you're going to be able to build on. Keep in mind, though, that this is a survey class. ELEC 120 is a survey class. So all this is a light sugarcoating of this topic. In future classes, courses, you're going to be able to drill down in further and explore these amplifier basics much more detail. So this is just to give you general overview, oversight. After completing this chapter, you're going to be able to describe the purpose of an amplifier, identify the three basic configurations of transistor amplifier circuits, identify the classes of amplifiers, describe the operation of direct coupled amps, audio amps, video amps, RF amps, IF amps, and operational amplifiers, and draw and label schematic diagrams for the different types of amplifier circuits. Amplifier configurations, the transistor can be connected in three different circuit configurations: common base, common emitter, and common collector. By using that term common, what we're talking about is one lead serves as a common reference point, and the other two leads serve as an input and output connection. So obviously, with only three leads to choose from, emitter, base, and collector, that's what gives us the three different possible combinations: common base, common emitter, common collector. Each configuration of amplifier can be constructed using either NPN or PNP transistors. It doesn't matter. I mean, it matters with what bias voltages we ultimately apply. But you could get the same results with either NPN or PNP transistors. The transistor, not transmitter, this is a typo. Transistor's emitter-base junction is going to be forward biased, which is nothing new, right? We always forward bias the emitter-base junction. That's how we turn a transistor on. The collector-base junction is always reverse biased. This shouldn't be anything new to you, because this is normally how we turn a transistor on. We forward bias the base emitter junction, we reverse bias the collector base junction. Each configuration, meaning common base, common emitter, common collector, is going to have advantages and disadvantages. The common emitter circuit is going to be the most widely used. It's going to be the most widely used. And we'll explore why in a bit. A picture's worth 1,000 words. This picture here really explains a lot. Let's take a look first at the columns here. We have the circuit type, common base, common emitter, common collector, and then input resistance or impedance, if you will. And as you know, impedance in AC is the combination of resistance and reactance. So we have, with a common base, a low input impedance, common emitter medium, and common collector high. Now, which is better, low impedance, high impedance, or medium impedance? Or is it irrelevant? Well, frequency is going to have a determining factor on it, but the most important thing for us to take into consideration is that we get the proper impedance matching. Okay? In order for maximum power transfer to take place, the internal impedance of the source must equal the internal impedance of the load. Remember we talked about that a little bit in ELEC 110? So in order for me to get the maximum amount of power from the source to the load, I need to match the impedance. So if I had a high impedance microphone, and I was going to attach my microphone to a cable and have that cable connected to an amplifier configuration out of a transistor, which configuration would be most desirable for me to use? High impedance microphone. This is not a trick question. If I have a high impedance microphone and maximum power transfer takes place when the internal impedance of the source closely matches the internal impedance of the load, which configuration would I want to use? High to high. Common collector. So an engineer designing that circuit, the first stage of that circuit, he or she would probably choose a common collector configuration to closely match the impedance of the microphone. Now the output resistance or slash impedance from a transistor configuration, common base, common emitter, common collector, will be in this column. So although the common collector has a high input impedance, it has a low output impedance. The voltage gain, common base is high, common emitter is medium. Common collector, check this out, voltage gain less than 1. You put in a volt, 1 volt peak to peak, you're going to get something out less than a volt peak to peak. That doesn't sound like it's amplifying voltage, does it? If what you're getting out is less than what you put in. However, for the common collector, the current gain is going to be medium. Common emitter, medium. Common base, less than 1. So common base is going to give us lower current gain, but high voltage gain. The combination, of course, of voltage and current in a circuit is what we define as power. Literally, voltage times current. So therefore, we could say that the common base has a medium power gain. Medium because it's high voltage and low current. Common collector gives us medium power gain, medium current gain, and less than 1 for voltage gain. But common collector has high power gain because it's medium voltage and medium current. So remember that slide where I said common emitter is the most popular configuration? This is why. This is why. Plus it's got medium input impedance, medium output impedance. It just lends itself to most applications. If you're in a lab using an oscilloscope and you were signal tracing, that's evaluating the signal from an input of an amplifier, comparing it to the output. Calling up the displays on an oscilloscope would look like this. Now for common base, we note that when we put a small signal in, we get a large signal out. Now, what is it that you actually look at on an oscilloscope? What are you looking at? It could be a sine wave, could be, so you're looking at the waveform, but what is it? You're looking at what versus what? Voltage versus time, very good. So you're looking at amplitude. So if you put in a small amplitude signal, you're going to get out a big amplitude signal. Common base, okay, common base. Voltage gain is high. So does that make sense? Does this output make sense? That you put in a small voltage, you get out a big voltage, common base, voltage gain is high? Okay. Common emitter. We put in a small voltage, we get out a big voltage, common emitter. We put in a small voltage and voltage gain is medium. So yeah, we're going to get out something bigger than what we put in. But what's unusual about this output? Yeah, this is inverted. This is phase shift. It's 180 degrees phase shift. So with a common emitter configuration, we're always going to get an inverted output. But it is going to be medium voltage gain. And then finally, common collector. We put in a small signal, and we get out a small signal. But if we look at this common collector, the voltage gain is less than 1. So is this illustration here really accurate? Okay. We really can't tell. I mean, it looks like it's exactly the same diagram. We'd have to get up and actually measure it. But it should be what? It should be smaller. Smaller. And then we note that there's no phase shift with a common collector output. The output's going to be in phase with the input. So the only amplifier that has phase shift is going to be the common emitter output. Amplifier biasing, all configurations of transistor amplifier circuits require 2 voltages. The emitter base junction is going to be forward biased. The base collector junction is going to be reverse biased. Both voltages can be provided by the same source, the same power supply. Thermal instability, of course, is a big problem with the utilization of semiconductors in general. Temperature changes cause the transistor's internal resistance to change. The bias currents then change. The operating point of the transistor shifts. Operating point means how much it's amplifying. Generally speaking, without getting too complex, what they're defining as the operating point is, you all know that a transistor could be used as a switch, right? It could be turned on and it could be turned off. When we turn a transistor on, basically what we are is we're saturating it. We're turning it on. We're using it as an absolute on condition. The other condition is where we cut it off. Between that point of saturation and cutoff is what we define as the operating point. So we get the transistor to kind of be turned on, not turned off, not turned all the way on, but kind of turned on at what we call the operating point. Therefore, when we put a signal into the transistor, that as that signal goes more positive, it turns the transistor on more. As it goes negative, it turns the transistor on less. So it's smack dab in the middle. If we were at saturation and we put a signal into it, any change in that input signal wouldn't be felt because the transistor is running at full throttle.
But what's making the transistor more on or off is the depletion zone, right?
Correct. And that depletion zone is changing based on the input signal of like you speaking into a microphone. When I speak into a microphone, it's creating electromagnetic energy, right? That's being transferred down the wire. That's going to be put into the input of the transistor. That small fluctuation is going to make that operating point change and amplify more, amplify less based on my speech pattern. And the key word there is amplify. So that's how speech pattern has an effect on the biasing of the transistor and thus the amplification of a signal. Make sense? So achieving that operating point is really critical. So obviously if temperature instability is going to cause that operating point to move. That's going to create problems for us. To compensate for temperature changes, we feed a portion of the unwanted signal back to the circuit input. And this is called feedback. This is intentional feedback. And this is good. It's not the kind of feedback you hear at a concert where, you know, check, that loud noise, obnoxious noise. That's not what we're talking about. This is intentional feedback fed back in to keep that operating point stable with a transistor. There are several classes of amplifiers. The first amplifier we're going to discuss is the Class A amplifier. The Class A amplifier is biased so that the current flows throughout the entire cycle. So that means if I put in a 360-degree waveform, we're going to get out a 360-degree waveform. Because of this behavior, this is going to have the most linear response. So it's going to be the most linear amplifier out of all of them. It produces the least amount of distortion. Why? You put 360 in, you get 360 out. Sounds like no distortion to me. Unfortunately, it's going to have lower output ratings. These are not going to be high-end power amps. These are going to be relatively low power amplifiers. They're the least efficient. Applications include use in radios, televisions, any type of analog circuitry. Class AB amplifier is biased so that the output current flows for less than a full cycle, but more than a half cycle. So you put in a 360-degree waveform, you get out something more than half, but less than full. Because you're getting out something less than full, more than half, this is going to produce a substantial amount of distortion. You put in a nice, clean, crisp circuit signal, you're going to get out something less than that. So it's going to produce some distortion. Class B amplifier biased so that the output current flows for only half of the input cycle. You put 360-degree sine wave in, you're only going to get half of it out. So since you put in a full wave and you're only getting out half, this is going to produce a substantial amount of distortion. Finally, actually that type will be used as output stages of stereo systems and public address amplifiers and many industrial controls. Finally, Class C amplifier, C as in Charlie, biased so that the output current flows for less than half of the AC input cycle. You put a 360-degree sine wave in, you're going to get something less than 180 out. Obviously, this is going to produce a substantial amount of distortion. This is used to amplify RF signals, radio frequency signals, used for radio and television transmission. So we're not talking about the audio or the video that make up a television signal or a radio signal. What we're talking about is the radio frequency that's being broadcast out. So like if you listen to the conservative broadcast of KISW 99.9 FM, the Rock of Seattle, that's what we're talking about. The amplifier that amplifies that 99.9 million hertz. That is typically a Class C amplifier. So if you looked at the schematic diagram up at the transmitter, you'd say, oh, wow, okay, yeah, this looks like a Class C amplifier because it's used to amplify the radio frequency, 99.9 FM, not the audio that you listen to. Obviously, if they're broadcasting out the audio using a Class C amp, it would sound like crap. Nobody would listen to that station. Now, since it's pretty obvious to us after looking at that chart, no one amplifier does everything for us. So typically what we're going to have to do is use multiple stages of amplifiers. Different stages to do different things. So we're going to have to couple the amplifiers, one stage to another stage to another. Even back in the day, in the 1960s, with an 8-transistor radio, 8 transistors were used to build a little AM radio. So that was 8 transistors that had to be coupled in some manner. So we have to use amplifier coupling, used to obtain greater amplification. The coupling method used must not disrupt the operation of either circuit. There are 4 methods that could be used. RC coupling, or resistive capacitive coupling, very popular, used primarily in audio amplifiers. And typically the capacitor is going to be electrolytic. And you need to be careful with electrolytic capacitors because of if you put it in a circuit backwards, it will explode, right? The low frequency limit of the audio circuit is going to be determined by the size, physical size of the capacitor. The high frequency limit is going to be determined by the type of transistor used. Because remember, transistor data sheets, they're going to show what the maximum usable frequency is. All transistors are not created equal. Another method of coupling that we could use is called impedance coupling. Impedance coupling. An inductor is going to be used instead of a resistor. We use the inductor because it consumes less power than the resistor, therefore having an overall increase in the efficiency of the circuit. Typically we'll use impedance coupling over only a very narrow band of frequencies that must be amplified. So if you have a narrow band amplifier, using impedance coupling sometimes is desirable for an engineer to choose. Transformer coupled circuits. Sometimes we're going to use transformers to couple one circuit to another. Can effectively match a high impedance source to a low impedance load. Remember before in lecture I was talking about a high impedance microphone? If you wanted to couple a high impedance microphone to a low impedance amplifier, you could use transformer matching. You could have an impedance matching transformer that you could utilize. Why is that so desirable? So that you get maximum power transfer. And you always want to get maximum power transfer. How many of you here have any speakers in your car or at the house or anything like that? How many of you want to get the maximum power to your speakers? If you want to get the maximum power to your speakers, you've got to effectively do impedance matching. If you don't, now, will it work if you don't? Yeah, it will work. And I've heard that from a lot of students. Well, you know, I just wired it up directly and, you know, it works good. No, it doesn't. Because unless you're matching the impedance, you're not coupling the maximum power from the source to the load. Now, sometimes, especially like with an audio system, you know, how often do you ever push it to the limit where you really want to do that? But still, if you don't, you're losing energy. You're losing energy, and efficiency is what it's all about. Another method is the direct coupled method used to amplify very low frequencies or a DC signal. Provide a uniform current or voltage gain over a wide range of frequencies. This type of coupling typically is not very stable. In summary, amplifiers are electronic circuits used to increase the amplitude of an electronic circuit. The transistor is the primary amplifying device. 3 common configurations: common base, common collector, common emitter. And by common base, common collector, common emitter, it means what are we using as a reference point for the input and the output. Common collector amps are used for impedance matching. Common emitter amps provide phase reversal of the input-output signal. It's the only one that inverts the phase. A single voltage source can provide the forward and reverse bias voltages using a voltage divider arrangement. A transistor amplifier could be biased so that all or part of the input signal is present at the output. Class A amplifiers are biased so that current flows throughout the entire circuit. AB, you put in 360, you get out 180. More than 180, less than 360. Class B, you put in 360, you get out 180. Class C, you put in 360, you get out less than 180. And primarily those Class C amplifiers are used for RF amplification, TV and radio signals. Coupling methods, RC, resistive capacitive, impedance, which utilizes inductor in place of the resistor, transformer coupling, and direct coupling. Direct coupled amplifiers are used for high gain at low frequencies or amplification of a DC signal. Anybody have any questions